reactivity versus selectivity. So reactivity is basically how you classify the hydrogens, and then selectivity is what halogen you're going to use. And so what CH bond is getting substituted. So the halogens, Cl2, Br2, F2I2, all react different according to the bond association energies. And then we'll summarize that in a table today. And so on Wednesday, we'll look more at reaction coordinate diagrams in terms of endothermic, exothermic. These numbers we put into a table look graphically if that helps you sort of learn it better. Any questions prior to starting? So the last slide from Friday was given this molecule with 4 explicitly shown hydrogen atoms, which one has the weakest CH bond? And so maybe the first thing to do is just by the carbon atom write the hybridization, and then we'll classify what type of hydrogens they are. So this one's sp2, sp3, sp3, and sp3. So it's explicitly asking you for the weakest. And so in the overall order of CH bond association energies, sp3, in terms of the bond strength, is less than sp2, is less than sp. So immediately, the sp2 hybridized carbon H bond is out, because that's going to be stronger than the other 3. Now you're left with 3 choices that are all sp3, so you have to classify them some other way. And I'll do this in blue. So we can say that one's secondary, and then primary. So a further classification how do I want to do this? I think I'm doing that right with the less than sign. So a tertiary bond is weaker than a secondary, is weaker than a primary. So right now we can eliminate the primary because that's going to have the stronger bond overall. And then we're left with these 2 secondaries. So if they're both secondary according to that classification, how do we then choose? One of them is special. So this carbon atom right here that's directly bonded to the aromatic ring is called benzylic. And so that's a special type of carbon. And so that's going to have the weakest CH bond. So when you apply the energy to the system, that is the bond that's going to cleave first. And again, since it's homolytic, those would be the 2 radicals that you get. And the reason that the benzylic radical is preferred is because it's resonance stabilized. So that pi bond can sort of hop out of the ring, and then you end up with a stabilized radical. So here's just one resonance structure for that. And then you can draw a couple more where radical and then pi bond system that will delocalize the radical from here to this carbon, then from that carbon to the third carbon over. So again, because you can stabilize that radical, that's a way to explain why that's the easiest CH bond to break. And I think that gives you a nice explanation of, once we start learning about reagents, how you can rationally predict what H is going to be substituted. Any questions before we really get into it? So for now, I would say the special ones will be benzylic and allylic. So benzylic is next door to the aromatic ring, and allylic is next door to an alkene. And so remember, it's the carbon that's bonded to that. So we're yeah.
How do you know which carbons are like special carbons that have different attributes?
So in the first part of this, we're talking only about CH to C chlorine. We'll get into the other halogens in a bit, but initially it's just for chlorine. In this table summarizes what we've learned so far in the semester. We're now taking an alkane to make a monohalogenated alkane. And so you can see from the carbon count increasing. We learned about nomenclature, molecular formulas, uniqueness, classifying methyl groups, methylene groups, methine groups, and then using that information to theoretically predict all the possible monohalogenated products. With butane, though, keep in mind that that's the carbon count which you start to have to consider stereogenic carbons. So when you get to that 2-chlorobutane, that's now a stereocenter. So that's the added layer from module 3. And maybe Wednesday or Friday, again, when we talk about the nature of a radical, since it's planar, when it is substituted, it will always generate a stereocenter based on the location of the single electron. So on Friday, we talked about using the table to look at these sort of half reactions of bond breaking and bond making. And so what I'm going to do on this slide is draw out what we know as the mechanism. And then on the next slide, you'll see it in table format where we actually put in the numbers and then start talking more about a chain reaction. So again, on this side, we were breaking. So that required the plus. On this side, we were making. That required the minus in terms of the sign for the bond dissociation energy. So again, free radical. The radical is just the dot or the unpaired electron. The chain is specific to this type of mechanism. So there's sort of sub-steps that occur in this. And a chain basically means it's going to repeat and self-propagate. So there's some terms associated with that. And the first one is initiation. So any frats or sororities in the room, this is not like hazing initiation. The initiation step is we're going to break the weakest bond possible. And so we go to the table, and basically what that is, it's going to be Cl2. We'll look at the specific numbers in the slide coming up. But on this slide, we're just going to show the arrow pushing. So we have Cl2, and remember, since it's homolytic cleavage, each chlorine is going to get an electron from that sigma bond. And so that will generate 2 chlorine radicals. Then the next thing that happens in the chain, that chlorine radical comes along and it's going to abstract a hydrogen atom. And since we're dealing with just methane, you don't really have a choice because it's a uniqueness set of 1. But again, when you get into the higher order alkanes, that's when you have a choice if it's primary, secondary, or tertiary, which one it's going to go after. So that radical will abstract that hydrogen and you form HCl. And then the other thing is you get the methyl radical. And then in propagation step 2, notice we haven't formed the chloromethane product yet. The methyl radical will react with chlorine. So you can think of it as abstracting chlorine, and then we form our product. And then chlorine radical. So what I want to highlight in with green here that chlorine radical is what propagates steps 1 and 2. So you formed it, and what happens is now that propagating radical will re-enter the chain over here and then react with another molecule of methane. So those 2 steps will continue on until all the methane is depleted, or if something else happens. So the other term that we'll use for a chain reaction is called termination. A termination step is characterized by that once bonds formed, another radical is not produced. And these can be basically anything. So for example, if you had CH3 dot plus Cl dot, that forms your product, but notice when they combine, it does not form another radical, so it's a termination step. Another termination step is, even though you see we want to form chloromethane, that's what we want as humans. And again, in the reaction flask, these things don't think, they do whatever they want. So a different one could be you have methyl radical, and then another methyl radical. So they would join up to form ethane. And so now you would be sad because in that flask you have methane and now you've produced ethane. So a chlorine radical can then abstract a hydrogen from ethane, and now you're going to get a mixture of things. And so if you're interested in like chemical engineering, that's what that discipline does, is designing reaction vessels and parameters to control that type of thing. Again, the goal of any chemical reaction is you want to produce one thing in 100% yield, because then you don't have to separate any impurities or byproducts. It makes life a lot easier. Another termination step, for example, could be just the combination of two chlorines back to Cl2. So in general, termination steps are not productive in propagating the chain. Any questions before we start looking at the numbers for this? So here that is in a table form, where in the last column where it says delta H, that's where we're just going to keep track of the math, and then look at the numbers. What's really important are the numbers for propagation steps 1 and 2, to see if the chain can live. Do the numbers jive with one another, or is it they're not going to be compatible to propagate the chain? So So in the initiation step, we want to look up the value for chlorine. Trying to calibrate myself on these signs. Signs always get me. So I believe on the left side of the little arrow we want plus signs. On the right side we want minus signs. So the next thing we want to look up is we need to break a CH bond in methane. The reason this gray line is here is because now we have to add two numbers to get it in the last column. So that was plus 440. And then we're making HCl. And then we add those together and we should get what? Plus 8? So in propagation step 2, we already know the value of that, so that's plus 243. And then we need to look up CCl in methane. So that's going to give us something. At negative 109. If I was in my office, I could do that in my head, but I'm in a class in front of people, so I'm going to cheat. So we're not going to worry about the termination steps just yet, but what I want to point out to you, what's important. Remember this propagating radical here. Cl dot, it's going back up into step 1. So overall for step 1, you have to have plus 8 kilojoules per mole of energy. Step 2 is producing negative 109. Because it's negative and it's more than 8, that step 2 provides enough heat or energy to get step 1 going again. So those are really the two numbers we're concerned with. Does step 2 provide enough energy to meet step 1's demands? So chlorine's nice. If we take 109 and divide by 8, so you get 13.6, so approximately 14. Step 2 is providing approximately 14 times the amount of energy needed for step 1. And what we'll see eventually in the next couple of slides is that these numbers will change for fluorine, bromine, and iodine. And really what, in the best case scenario, you want those numbers as sort of matched as possible. So we'll see that, there's extremes from fluorine to iodine as we look at doing that same exercise. The termination steps, you can look up those numbers and stick them in there. It's good practice for finding them on the table, but we won't consider them now. Really, we just want to see is when we start substituting the halogen X2, is it going to propagate the chain? To switch back and forth here, hopefully I get the right numbers. And so that's right there, 243. So that's right there. So that's negative 432. So negative 352. And so here is the table filled in with better font than my handwriting. So again, there's 3 things you need to be aware of. The initiation, that's typically you're breaking the weakest bond in there. That forms a radical that goes into the propagation. You really have at least 2 propagation steps. If there's any polymer science students in the crowd, you'll study radical mechanisms more in depth. And there can be more than 2 propagation steps. But for this class, it's just pretty straightforward with 2. And then I've shown 3 termination steps, A, B, and C. There can be more, again, because the complicating factor is really that. When you start producing other alkanes in there, those can form carbon radicals that can get substituted, and then now you're dealing with a mixture of things. So here is a general table that I'll let you fill the numbers in. I'll show you the numbers on the next slide, but you can work through the exercise, see if you get those same numbers to follow the logic. But basically, we've generalized the reaction now for any halogen X2, and that's what you see in the table, F, Cl, Br, and I. And again, you just go to the table of dissociation energies, you do the same thing. Really what we're concerned with are these two entries. Is that green row going to supply enough energy for the red row to continue the chain going? And then the last row there just says propagation step 2 divided by 1. It needs to be in slight excess, so that is supplying enough energy. But then again, you got to make sure that the signs are correct, that the heat is actually evolved, that it can go back into step 1. So here's the table filled out. So we did chlorine. You should do F, Br, and I to make sure that you understand how we got those numbers, but it's the same thing. And so let's just look through those 3 other halogens and compare those 2 rows. So for fluorine, propagation step 1 evolves negative 130, so it's already negative. Step 2 is also evolving energy, negative 302 now. What that is telling you is this is evolving a lot of heat, but that's also evolving heat. So fluorine ends up being pretty indiscriminate when it's sort of scanning a molecule to do a substitution. And because so much heat is evolved, essentially any sort of CH bond will be substituted for F. And a lot of this is known. How many people cook regularly? Do you ever make scrambled eggs? So you notice there's a difference between a stainless steel pan and one that's coated with a polymer. A stainless steel pan, you'll get stuff stuck to it that's damn near impossible to get off. The other ones that are coated, the coating is a fluoropolymer. So it's really long hydrocarbon chain with a lot of fluorines on it. And so the chemical company DuPont was the sort of first to discover this. These fluorinated polymers, and that helps it make a non-stick coating. So you just tilt your pan and the egg slides right off. But fluorination, as you see, it needs to be controlled because it's indiscriminate. Chlorine, as we said, has a good match between heat evolved and heat needed. But now when you look at bromine, that first step requires plus 74. The second step evolves minus 100. So the ratio of that is 1.4. So it meets the energy demand, but notice it's much less than chlorine. And then for iodine, step 1 requires plus 142, but it only evolves negative 89. So it does not meet that demand. So for synthetic purposes, you can't use I2 in this reaction. It just will not progress. So fluorine it's like the Goldilocks porridge here. It's fluorine is too much, iodine's not enough. And then chlorine and bromine are really the ones we're going to talk about. So chlorine is said to be promiscuous and non-selective because that amount of heat really will not discriminate between primary, secondary, and tertiary. Bromine is more selective. So it's really going to follow that order of tertiary, secondary, primary. And sort of prove that over the next couple slides, we're going to look at the differences between those types of hydrogen. So we'll fill this table in on this slide, but the subsequent questions are just the ones I'm going to ask now. And we did this on Friday, but now we're going to dig a little bit deeper into it because we're going to actually look at the observed yields and compare them to the theoretical yields and see what the difference is. So our first row here, number of each type. So we have C3H8, so we need a total of 8 hydrogens. So for the primary, we have 6, the secondary 2, tertiary none. And then the percent is just that number divided by the total. So 75, 25, 0, 100. So the little note there is that percent is telling you that's what you would expect to see in the product distribution if you only considered the statistics of the hydrogens present. So this question was B620. This was 75-25. That's what you would expect based on the percents of those hydrogens. So again, there's the summary of that. And on the next slide, we're going to look at what the actual percent yields of primary versus secondary are. And you see that they're not really anywhere near 75-25. So everything below this line is new for the discussion here. So as highlighted in green, it says observed yield. So you get a 45% yield of the primary substitution product and a 55% yield of the secondary. And you can see it doesn't match the theory. And so we just do a little bit of sort of division, multiplication, addition, subtraction to come up with these other terms. So the next one says ratio of observed yield. And all we're doing there is dividing each by 45. So that's the lowest one, so that gets us a ratio. So we get 1 and 1.2. Whereas, as before, you would have thought it should be basically a 3-to-1 ratio. Now, the new term here is this. So relative reactivity. And we're defining that as the observed yield divided by the number of hydrogens. So the 7.5 comes from (45) divided by 6 gives you 7.5. 55 divided by 2 gives you 27.5. And then the last column, you just take those ratios. So 7.5 divided by 7.5 gives you 1. 27.5 divided by 7.5 gives you 3.7. And the grand conclusion here, or the takeaway, is that a secondary hydrogen is 3.7 times more reactive than a primary one. Again, the caveat for that is right here when we're considering chlorination. So again, just to beat the dead horse here, what we're trying to explain is why the observed yield looks different than the theoretical yield. And the meaning is that the nature or class of the hydrogens matter. So if we do the same analysis with propane, except now we're going to use bromine. So Br2 as the halogenating agent. Notice the observed yields here. The secondary bromide is now present in 97%, the primary in 3%. So you have about 33 times more of the secondary than you do the primary. So again, if you were expecting a 3-to-1 ratio, you see about 1 to 32. The relative reactivity, you take the yield divided by the number of hydrogens, then you normalize that. And you see that when you use bromine, the secondary hydrogen is now 99 times more reactive than the primary. So it not only matters the types of hydrogens in the molecule, but what halogen you're using. And again, we're really focused on chlorine and bromine for the purposes of this course. And this slide asks, now what about a tertiary hydrogen? So for that, we have to switch the molecule so that we have one with a tertiary hydrogen. And the substrate that we'll look at is 2-methylpropane. And so we do the same analysis. We have 9 primary, 0 secondary, 1 tertiary, for a total of 10. So in theory, we would expect the substitution products to be 90%, 10%. Of those two products. So this question was B. Well, this one will be D, 90-10. again, there's the summary. And again, what you'll see is the observed yields do not match the predicted yields. So the same two type of analysis, chlorine and then bromine will be on the next slide. So again, pay attention to the observed yields. 63 to 37. So we would take each of those, divide by 37. That gets you the next row, which is the ratio. The relative reactivity, you take the observed yield divided by the number of hydrogens. So notice that again, the tertiary is the greater number here. So when you normalize it, we see that the tertiary hydrogen is 5.3 times more reactive. So based on everything we've seen with propane and 2-methylpropane, the trend, it's telling us that when you analyze the molecule, a tertiary hydrogen will be substituted preferentially over secondary over primary. The same analysis for bromine. What you see in these numbers for the observed yield is that the bromine is indeed a lot more selective because the numbers change quite a bit. So the tertiary bromide you see present in 99% and really only a trace amount of the primary. When you run through that whole analysis, you now see that that number is pretty big, 990. So the reason this is important is, and I'll use the next slide sort of to demonstrate this. We're taking an alkane and we want to stick a halogen atom at a specific location within that alkane because, again, we're going to use those haloalkanes as starting materials for the next mechanism that you learn in this module. So I did not include this in today's lecture, the reaction coordinates that actually diagram this stuff out graphically. So I talked way faster than I thought I would, but what you'll see when you compare the reaction coordinate of chlorine versus bromine, the energy hills you need to sort of climb in each case. Again, to go over the transition state to get to the products, how they differ in terms of those numbers overall for steps 1 and 2 in the chain reaction. So one thing you can commit to memory at this point is this trend. So to make your life easier, you know, again, the module exams, you have 24 hours, you can use your notes, your book, etc. But, you know, at the final exam, it is you and yourself and a pencil. So you have to relieve your mental burden of trying to memorize 12 chapters. Committing a couple trends to memory is really going to help you navigate that final exam. So, any questions before I draw some stuff? I don't want to cheap you out on 14 minutes, so we'll take a couple more minutes and probably end a little bit early. Any questions before I do some drawing? So let me just again demonstrate. So say you had 2-methylbutane. And so the first thing, if you wanted to predict what products you could get, you'd have to do the uniqueness, and then you're substituting at each unique set. Then you're asking the question, does this form a stereocenter, yes or no? And so that'll increase your total number of products. So let's do that. We'll draw some things out, and then I'll point out why this is relevant for the next substitution mechanism. So for this, we have 4 unique carbons, 4 unique sets of H. And then that would be the ratio. So you could even further classify this as those 6, 3, and 3, those are primary. These 3 here, that methyl group, those are also primary. The 2, that's a methylene group, those are secondary. And then finally the 1 there, the methine, that's tertiary. And so we've done that, and we say, well, the easiest bond to break is the tertiary one, so that should be the major product. We can draw that out. So maybe to cover my butt, I'm just going to call it X. So that'll be chlorine or Cl2 or Br2. And then if you formed minor products, the next thing that would form would probably be at the secondary center. So is this carbon a stereocenter? So you have a halogen, a methyl, an H, and then an isopropyl. So that's going to be a stereocenter. And again, that's what I mean by that would then increase your total number of products because you would then get the R and the S enantiomers there. And so the other minor products would result from substitution at the 2 other primary sites. So let me ask this. Is that carbon right there a stereocenter? No, because it has H2. Is this a stereocenter? So, no? You don't think so? That ends up being a stereocenter because you have methyl, and now this is its own thing, right? H and then ethyl. So even though that methyl group existed there, you've now differentiated it from the one that was substituted. So that does become a stereocenter. So that might be a little bit harder to spot because nothing sort of happened over there, but it's still in there, right? And so just to wrap this up, again, bromine is definitely going to give you the tertiary as the major, but since chlorine was a little bit more indiscriminate, you'll probably get a larger percentage of those minor things. And then again, once we have these haloalkanes, we're going to learn two mechanisms, SN2 and SN1. And those are both categorized according to the class of the haloalkane. And then notice they run in opposite directions. So as I said, we're far enough away from the shore, which is Gen Chem at this point, now into strictly organic stuff that the stuff from modules 1, 2, and 3 are just building on each other. And the trends, I think, in my opinion, are the best way to help manage all the information that's going to be dumped on you in terms of predicting reactivity. So again, that's where we're going in this module, but now we know how to make these different classes of haloalkanes. And then on Wednesday, we'll look at the energy coordinates and then other issues with stereochemistry.